So I will introduce our next speaker, Dr. Menes Gaur. Dr. Menes Gaur is an assistant professor of computer science at the University of Maryland County, UMBC. He leads the knowledge-infused AI and inference lab in collaboration with Kennedy, Krieger, Mayo Clinic, Bosch Research, and Samsung Research. He's working primarily on consistency, reliability, human explainability, and safety in machine learning algorithms, and a model with structured and procedural knowledge for natural language processing. Menes received his PhD from the AI Institute at the University of South Carolina. He has received the AAAI New Faculty Award, the Turing Fellowship from the Alan Turing Institute, the AI for Social Good Fellowship, and Google Data Science Fellowship. So let's welcome Dr. Gaur.
Okay. Okay.
Let's just your.
I'm audible?
We hear you.
Okay. Oh. Just a minute. I think. Okay. Oh, perfect. So. Okay. I'm audible now?
Yep.
You can hear me, right? Okay, cool. Okay. So thank you all for being present, and thank you, Ramana, for the invitation. And today's talk, I want to talk about a structure that I have been working recently on the context of large language models. And essentially, it talks about a research that I've been doing concerning with respect to the NeuroSymbolic AI in specific. So the outline of my talk today is going to be a very high-level touchdown on the neurotechs or neurotechnologies, and a very interesting work that I've been doing that the folks at CMU are doing with respect to the intersection between vision and language and the fMRI, which is, they call it as a NeuralTaskonomy. And we'll then talk about a segment of large language models. What are the hurdles that exist in the adopting of these large language models? And why do we really need the neurosymbolic AI or neurosymbolic structures of these large language model training? At the end, I will just give a conceptual framework that is essentially a work in progress. And much of this work are essentially are under review at the moment. So I will just try to be more at the conceptual level and motivating the thought of the neurosymbolic LLMs. Okay, so pretty much everyone knows about the neurotechnology in the audience, and we know about the people talk about the use of these technologies to understand how the human mind works, and how these technologies can be translated, their signals can be translated into text and then can be connected with these language models over the time. That's what the trend is going eventually. Right. So as the previous speaker might have also motivated that thought of connecting large language models and the neurotechnology. One interesting fact that I want to bring into the picture is that our human brain, our human mind actually lacks context until unless it is explicitly being provided for various functionalities. And we generally define these context as experiences or the skills that we have gathered over the time from various activities. Right. And what essentially we really want to, what we are doing as for instance, let's take an example of you guys listening to me and connecting your experience, your understanding with the terminology of neural tech. You are actually defined. So this is what we consider as a notion of consciousness, right? Being very conscious, being very vigilant, understanding what is right, what is wrong, understanding that at which point in time, which answer is more suitable and which answer is not suitable. So these characteristics are something that we have gathered over the time through our experiences and through our understanding, whereas we do not have this similar technologies in the large language models as we progress with them. For some of the essential challenges that we have identified as that the emotions, the morality, the biases, and the consistency, and the chance and the possibility of delivering explainability are some of the stuffs where we really want the large language models to progress, and those are the points that are at present are very poor at the form in the form of ChatGPT, or even a higher version of it, let's say the GPT-4. So let's take an example of why we are really delving into this notion of connecting large language models with fMRI information or with the brain technologies. So this is something, a very interesting work that was done at Carnegie Mellon, which talks about or which introduces the notion of NeuralTaskonomy, right? And there was a data set which was the Bold 5000, which had this information of different scenes and images and connecting them to the fMRI scans. So what this study did was they looked at different parameters of those images and those scenes, which essentially being seen in a convolutional neural network. And they want to see that the prediction of the CNNs are matching with the predictions that a human mind is making, right? And they want to find the connections between these different regions and the regions in the brain, right? And what they have understood that there is certain disparities that exist between what the brain classifies at these points and how this CNN is doing the classification. So what you see on the right is essentially a dendrogram, which is nothing but a clustering mechanism where the brain clusters the jigsaw and vanishing points and denoising and all those activities together, whereas the taskonomy, or basically the CNN part, actually considers them as in a different group altogether. So this structure, the study was essentially an interesting way where they looked at how the different brain regions are looking at the task in the scenes and the images as compared to what CNN is looking at when it is being given those images and the scenes. So this was the vision part of it. So one interesting factor of the taskonomy came up was that the underlying phenomena is that the task relationships do exist, and brain exploits this kind of relationships, and so does any neural network that exists. So CNN very well looks at the relationship between the different tasks. They can be computationally measured. This is something that they have found through various experiments on the CNNs, and they found that fine-tuning, transfer learning, meta-learning, or meta-transfer learning, or reinforcement learning with human feedback are some of the popular ways where you can tune these large language models using the predictions that are being driven in the brain responses, right? And what they have found was that these informations that has been predicted by the brain and that has been predicted by these neural networks, they actually share a space where they call it the embedding spaces, where they are connecting these two information and finding the similarities. Now, this underlying study, which happened in 2019, brought into another set of a study in 2022, which talks about the language of this same experiments. They translated the same structure of experiments that happened in the vision onto the language side. So there was two interesting data sets that were developed. One is the subjects were asked to read the sentences and the paragraphs, and they want to record what are the different activations that are happening in the brain. And as opposed to the second aspect was when they were asked to give us some narratives or generate some narratives after listening to some stories. So what they have found in this experiment is that to a certain level of correlations do exist between how humans have how the human mind completed those stories as opposed to how the language models are comparing those or are completing those stories. So what you see on the right is essentially a two-fold evaluation. So one was a cosine similarity, which is essentially on the top box, and the Pearson correlations, which is underneath. So what they found was that vision and the language are suddenly like they are not super confident in terms of the cosine similarity. So when I say cosine similarity, it can be assumed to be very simplistic way of semantic similarity, right? So what they found was that the semantic similarity was relatively low, whereas the correlations in the words are pretty much high. That means that if the words that has been taken by the human mind is pretty much the similar words that the BERT, basically a transformer that they have used, was similar, having a similar correlations. But when you look at the understanding of the sentence, whether those sentences mean the same thing, that's where things become very, very weak. That means that even if we have the same generation, we don't have the same semantic meaning. So this begs a question, a very interesting question that comes and has been there from the early this year, is that do the large language models and actually understand what they're generating, or are they just generating some words which accidentally seems to be more fluent and coherent rather than making any sense to the human users? So with this, but there is a huge possibility of the work that have been done recently, and those works are at the exploration levels, which one of the things that actually caught my eyes in August essentially was this study at the very end, which is on the semantic reconstructions of the continuous language from the non-invasive brain recordings. It was very interesting. The found that these the paper actually made a very modest claim that at the moment the ChatGPT is not really prepared for more critical tasks or more sensitive tasks. There have been a series of cases where they give this the ChatGPT was able to give an exact response, whereas those exact responses were not consistent. So if a small tuning, a small change in the input can actually change a huge structure of the language in the GPT. And it also highlights some of the errors, which is meaningful. That means that there were cases where the words used by ChatGPT did not make sense in a sentence, but there seems to be a sequence of sentences that have been sprouted by the GPT model. So with this in mind, there were a series of work that recently being started at Stanford, which they call it under the hood of called LLM benchmarking. And what they have been doing is that rather than practicing these large language models as an independent models, like, okay, you try it out with GPT-4, you try it out with GPT 3.5, you try it out with Google Bard. But what they have been looking at is that these models together seems to be doing a good job as opposed to letting these models run independently. So what they have been exploring at the moment is the concept of ecosystem graphs, which is they are looking at how these models together provide a more cohesive response as opposed to these models being experimented independently. So this is a very interesting framework or a benchmarking framework they have been developing recently, which is called the holistic evaluation of these large language models. And various cases in various scenarios, they have been talking about issues like story completion, where language models are not capable of completing the story with a positive ending, whereas a human in a healthy state does. Whereas if you compare a human with some mental issues or mental health issues, definitely there is a certain level of negative story ending that exists, but a majority of the cases, large language model tend to complete story with a negative ending, until unless you are explicitly instructing the language models to complete the story in a positive ending. There's another framework that that is also under in progress, which is talking about these large language models evaluation network, which is essentially looking at whether these models are able to hold morality in the generation. Are their emotions matching with the emotions of a human? So the human was giving responses, and these large language models are also giving responses, and they want to see that whether those responses have the similar emotions or they have a differentiating emotions as well. And there's another set of benchmark that I built last year, which is essentially looking at these large language models with the perspective of various critical applications like summarizing clinical interviews, looking at how the users generated content changes over the time with severity levels. For instance, let's say you started, you're playing a game, and suddenly there are violence that starts to show up in the game. How does your mind does those assessments of those violence, and how your mood or your emotion changes over the time? And there are other cases where we looked at how students write the stories as opposed to how the large language models or LLMs are completing the stories as well. So in all of these experiments, one thing was very interesting and very challenging, which previous studies at the intersection of brain responses and the large language models were missing, which was the knowledge component. So when I say the knowledge component, that most of the benchmarks that have been played around with ChatGPT do not really require external knowledge at all. So for instance, let's say we take an example where we gave a model a query and we gave a truthful source and asked the model to give a response. And that's fairly easy because that truthful source is already provided. What if the truthful source is being replaced by something of fake information? The model tends to utilize that as well and give you a response. So no matter what happens, no matter what situation is, ChatGPT will always give you a response, right? Whereas in certain cases, certain responses are not desirable, or there are some certain guardrails needs to be established. So essentially what we did was we started exploring the benchmarking of these large language models on the mental health specific tasks. So what we were doing was that we were enforcing these large language models that whenever they are making any justification or any response, we want them to explain what their responses look like, right? And second task was essentially looking at these large language models and asking them to populate some of the clinical questionnaires which clinicians uses to examine the mental health. So some of the tasks that on the explanations and reflective question answering opened up the new set of challenges for the large language models. So at the moment, if you see ChatGPT or GPT 3.5, essentially, they do not ask a follow-up questions. They do not ask you any follow-up questions essentially for completing a response. So these scenarios actually opened up a new set for the benchmarking these large language models. So what underlying thing was that we found is that there is a certain component that we really want to investigate in these large language models. And this is not essentially only in this LLMs, but across any language model that have been built so far, back in from 2016 up to now. So that was the concept that we called the rule of thumbs, which is a very simple and layman term of calling a concept called tacit knowledge or learned knowledge. So what is this rule of thumbs concept looks like? What exactly this rule of thumbs are, right? So when we train these large language models over the time, for various cases over various data samples, these models tends to learn a series of different rules. These rules are learned over the data, and the hypothesis is that if these rules are correct, if these rules that the model has learned over the time are correct, then they should be able to give a more decent response with those rules of thumbs. We really don't need these large language models to be trained over multiple samples or multiple data sets or even large scale data sets. We just want their rule of thumbs to manifest the same level of intellect as these large language models are having over multiple rounds of training. So the idea of in a nutshell was that ROT tells the LLMs that which generation is right or which generation is wrong and how to handle such a conversation. And this seems to be very important in the context of mental health conversation, where pretty much everything what is right and wrong is being described in the context of mental health. Another context is the moral conversation scenario, where you really want to figure out that whether this particular sentence or particular generation is morally sound or morally correct as opposed to morally wrong. The third component is personalization. If you have been seeing ChatGPT so far or GPT-4, certainly personalization is not their major forte, which is essentially one of the component where the human mind as well as the large language models can find a synergy together. And the last one is essentially the bias aware conversations. Our human mind pretty much know which sentence is biased and which sentences is not. And for the large language models, it is very hard to figure out that which sentence is biased and which sentence is not, and how to provide a response that is most bias aware. So a very interesting example, a study that have been done at University of Washington talked about this kind of a scenario where they tuned these ROTs to enable these large language models give a more stable and more precise and more polite response, as opposed to just generating a very abrupt response. For example, if you see what would the society be like if everyone was bisexual, the reply was that I don't think it would be a good thing, right? And bisexual people are more likely to cheat on their partners. Whereas the ROT says that you shouldn't judge people negatively based on their sexual orientation. And that actually utilizes the model that has been used by the model to actually revise their answers. So does such rule of thumbs, we assume that they are part of the large language models when they're being trained, but essentially we also can provide them as an additional instructions for them to follow the desired outcome that human would accept. So we actually explored this this kind of an issue over a larger scales with different large language models. So one thing that we found that in the context of ChatGPT, even if you just rephrase the sentence, let's say I rephrase this point that is violence necessary part of the life? I ask it today, I ask it tomorrow, I ask it day after tomorrow, I get different response. So this certainly tells us that there is certain sort of inconsistencies that exist in these large language models, and there is no way to cure it until unless you open the box and you understand the internal dynamics of these large language models. Another scenario that we found that I gave a question to this large language model, like the GPT 3.5, and I explicitly gave an instruction which follows by the definition rule of thumbs that the output should be a more honest outcome, which is should be very favorable. But after certain period of iterations, you tend to find that the information is the generated information is certainly not the correct one, and it's going out of the control. So this scenario, what I have seen is I scaled it across 80,000 queries over a kind of a week period of time, and we tested 80,000 queries over 1,000 times across these 7 different large language models that have been developed so far, which is coming from FLAN T5 to GPT-4. What we were looking at is that the FLAN T5, Vicuna, and Falcon, which is essentially or Llama, tend to have a more higher tendency to provide a more incorrect or unsafe responses, and tend to show more inconsistencies compared to Llama 2, GPT 3.5, and GPT 4. One interesting thing was that Llama 2 was able to provide its own opinion, which GPT 3.5 and 4 could not. And that opinion was pretty much a sense of bias that the Llama 2 has based on its own generation. Another interesting factor that we found was that when we looked at their ROTs, we asked each of these large language models to give us their rule of thumb, what they have learned when we did this 80,000 scaling over 1,000 different iterations, that what they have learned from this 80,000 queries. And we were able to figure out that there was no similarity between how they were following the rules for making a generation compared to what the human would do when making those generations. So the intersect between these two was less than 40%. And that tells us a huge story that even if we are getting the right response from GPT-4, it is not legitimate to figure out that that response will also be available to every other person in this world who have been using that same query or similar query on the same GPT-4 response or same GPT-4 system. So that was a scaling process, and this experiment was done on a distributed server where multiple people did some same querying over these 7 different large language models. So what we found was there's certain level of issues that occur in terms of which can be represented as hurdles in adopting these large language models. The first one was a consistency test, right? These models were certainly not consistent in their responses. Even we have semantically equivalent questions, you will be getting different answers for different questions. Second concept was the reliability test. If I take Llama 2 and if I take GPT-4, I get different responses. If I take Google Bard, it's completely different response. And there is no connection from where this responses is coming from. If you reason these large language models for where the source of their responses, it is certainly not possible to give the response. Certain improvements have been done in terms of Google Bard, which is using Google search engine, and the ChatGPT, OpenAI ChatGPT using Microsoft Bing. But when you look at these search engines, you have a question of privacy and user safety, because you never know whose response is being used from formulating that particular responses. The third point was explainability, where we were not able to get any close to how human would explain an outcome compared to what a language model is explaining in outcomes, right? Because the consistency is not there, the reliability between different models is not there, the explainability is certainly not a point that can be trusted at the point of the large language models. The last point was the safety test, where we want these large language models to follow certain constraints or certain rules that clinicians are in the context of mental health and some kind of social scientists who are following the moral principles are to be followed. So what we found was there are three key aspects that the large language models at the moment go haywire, which is groundedness. They are certainly not grounded in the domain. They are not instructable. That means that even if you instruct them, they tend to still go out of their path and generate some weird outcomes. Alignment, even if you say that the model to generate the response in a very polite and humble manner, it does not demonstrate the same level of politeness and humble manner as a human would does. So that scenario talks about these 4 points essentially combined together to demonstrate a trustworthy framework that is still not showing up in the large language models as we as we say in the context of GPT-4 or GPT 3.5. So this is where we talked about a kind of a NeuroSymbolic LLMs. So certainly because we really are fascinated by how the neural networks are doing, how they are perceptive. But there is also a symbolic nature which is demonstrated by the human knowledge and the human constraints and even the consciousness that the human follow to design a more specific large language model that works at the intersection of symbolic knowledge and the neural network structures. So the inspiration that I had was that I'm coming from a community of knowledge graphs where we construct information from the graph. So we have constructed knowledge graphs for UMLS, the Mayo Clinic, from a drug bank and various other sources. So these knowledge graphs, essentially what they does is that they look at the intersect knowledge. So when you are answering any questions, your human mind looks at all your points, all your experiences that have been gathered over the time that are constructed as a graphical structures. And we want to use that same graphical structures to be a part of these large language models as well. Another component that exists in real time is process knowledge. If you are being asked to formulate a particular answer in a particular sequence with certain guidelines and certain procedures, it is very difficult to make the large language model to follow that same procedures as well. So process knowledge or procedural knowledge is still a far-fetching structure attribute for these large language models. The third component that I want to talk about is certainly the knowledge as a constraint. What is right, what is wrong, when that particular point is right and when that particular point is wrong is certainly not a forte of a large language models at the moment. And this is where a lot of these challenges arises, where the desired responses from the large language models are not fruitful for any critical task, as rightly said by the co-founder as well. So the NeuroSymbolic LLMs, as I define, are grounded, are instructable, and are human aligned, which exploits this domain and expert design knowledge to carry out inferences, because we really want to focus on the inference part of these LLMs on known and unknown problems with trustworthiness. Essentially, because we really want them to be consistent. I should not be like, I'm running a query right now and anyone in the audience is running in a query at the moment, and we are getting two different answers, right? Because human does not do that way if we have the similar query. The second thing is the reliability. Multiple language models behave independently. That means that there is a mixture of expert that can be designed so that these large language models can work together as a whole. The third component is certainly that we talked about is concept of explainability, that when the outcome is explainable and can be understandable by the end users. And the lastly is the safety, where we want to model to follow the certain guidelines and certain procedures so that anything that is right and wrong is being decided inherently inside the model and not putting up a guardrail as what ChatGPT or GPT 3.5 is doing at the moment. So what we have defined in the groundedness is that LLMs uses this domain knowledge. Alignment is talking about the use of the specifications or these guidelines. And the instructable means that the model is ensuring that those instructions and those guidelines are being followed at all times, irrespective of the scenarios, irrespective of the domains, and giving plausible explainability when required. So this structure are actually designed into a schematic in a following sense. So when I say groundedness, I am actually talking about a scenario where a large language model talks to a kind of a retriever or a database where it can understand what knowledge or which particular information is to be given to the end user. So when a human and LLMs are interacting with each other, it is important for LLMs to connect to a retriever store so that right information is being given. A very interesting application, I don't recall at the moment on my presentation, but it came from the I think 3 months from now. There was a very interesting video on brain computing interface and ChatGPT online on YouTube, which I think around 3.5 thousand people have 3.5K people have actually viewed it. A very interesting factor of that video was that there is a paper called Reflexion, which is a very interesting paper recently in Europe's 2023, and that paper has a very different abstract and very different description. It has no information on semantic memory. It has no information on episodic memory, right? And certainly it was not talking about anything on the brain computing interface. But that paper was included in that video, and the person was asking ChatGPT to explain that paper, and what it has explained has nothing to do what actually the paper is saying, right? So there's a lot of disconnect between what a ChatGPT is giving or what GPT-4 is giving, as opposed to what human is expecting or from that paper. Another component that we found we want to design is the alignment problem, where we really want this humans and the LLMs alignment should be very specific. So when I say alignment, let's say if a human says that I want to give a response that is more polite and consistent, and it should be more favorable to the audience or to the person who's listening, that kind of synergy is not there in the LLM. So human moral values or human values, which is essentially a very important component and is very subjective, is still far from being implemented in the LLM structures. And the last part is that if the in your groundedness and alignment are together, we really want the model to be instructable. So when I say instruction, that means the model is following certain kind of guidelines and certain structures for making the decisions and the outcomes. Okay. So this grounded and instructable work are something similar that we did, and is something a research that I did with Samsung Research America, which is taking an example of a very large language models. I'm talking about this study in the early of 2022. So certainly I do not have access to ChatGPT at this point of time. But and certainly this is at the moment, it is fairly workable in the ChatGPT as well. So we took T5 large and we asked the T5 large language models, which is just a generator model, to give a response to ask follow-up question to a person who has been saying that he's hopeless and he's depressed and he needs some help or some advice, right? And we found that the generation that the model has given was nowhere close to what the end user is asking, or of what would be a more legitimate question answering scenario. What we did was we simply pulled together this generator with a retriever at the back, which is very similar to the previous architecture that I was showing you. And the task was that now the generator communicates with the retriever to a reward function, very similar. You can assume it to be reinforcement learning structure. And we were able to figure out that the generations were a little bit better, but certain generations were unsafe, right? Because the model now learning to generate new questions to be asking to the user, right? And then what we did was we looked at another scenario where we use this kind of a graph structure that I was talking about, the knowledge graph, and you are using that to structure the scenario. So what we saw that by using this graph, we were able to at least capture the context which the large language model was not able to capture. The second is that whatever the generation the model was giving had some semantic connect, were not random. They were connections between what the model is generating. And we were not giving any instructions. We were not giving any sort of rules. It was just model by itself using the graphical structure knowledge. And the second thing is that we given the instructions to these models as an evaluator network. So the evaluator network over here, if you see, is essentially just an instruction that gives through the neural generator network to guide what should be a logical order in which a particular question needs to be asked. So this seems to be a very interesting preliminary experiment that we found and seems to be was the state of the art in 2022 on how we can have a model that can capture the context promptly, can ask you a certain set of questions in a very semantically sound manner, and they're relatable, and in a sequence that makes logical sense. And then we extended this work essentially with a different scenario where we put those guidelines that I was talking about, this kind of procedural knowledge as an intrinsic component within these large language models. So this is a work in progress at the moment, and so far the results were spectacular in the context of various scenarios. And this is what you see over CAs are the cross-attention blocks. That means the model examines that whether the generated response answers these questions or the generated response is indifferent to these questions. If it is indifferent to these questions, it won't be given as an outcome. That means the model learns to refrain when to give a response and when it should not give a response promptly. And we found this to be very synergistic with the explanations, because when you make such kind of intrinsic developments in these large language models, they tend to give a good explanations compared to a model that does not have this kind of a properties. So this structure that I showed you in different segments actually boiled down to a very modular architecture where we have a knowledge component, we have a neural network that we are still using, that's the T5 for instance, or GPT 3.5 or GPT 4. We're using them as it is. But what we are doing that is that we are enabling these language models to learn over the context, to find the right context. We want them to follow the logical order that a human follows, and also give the wider possibilities of responses rather than just giving point blank answers. So that possibilities allows you to explore what is right and what is wrong, as opposed to give a point blank answer, which the GPT-4 or ChatGPT is doing at the moment. So this structure is essentially a more deeper manifestation of what I have been talking about throughout my talk. And we have been focusing on this kind of a training of the NeuroSymbolic LLMs. And I will just take 2 minutes to give a deep dive into this particular architecture. So if you see on the left-hand side, I started with an input. And what we did was we are training these large language models, not one, but m different large language models together, with paraphrasing the input and making some adversarial changes in the inputs, so that the model knows what is right question and what is a wrong query. And we are trying to utilize the knowledge structures to elevate these questions to a more conceptual understanding of what these questions are. So that means that every query that the user gives, the model learns to add certain context to this query by using the knowledge structures. And we train down these models in a generative evaluator network. Evaluator is because evaluator allows you to do instruction tuning inside your neural network. And then once it follows the instruction tuning, we are now examining those instructions and instruction following nature by using a transformer, which is at the moment is GPT-3. So certainly this would open the scope for improvement of these large language models towards better explanations, better instruction following natures, right? As well as holding on to the consistency, reliability, and safety part as well. So this structure at the moment is what we have been working, or we are working at the moment. And this structure is essentially the one which is under review at AI Mag, which hopefully will be released by the end of this year. And we have been doing a series of events on this NeuroSymbolic LLMs. We started NeuroSymbolic LLMs in 2021 in the Knowledge Graph conference. Then we extended this to KDD. We have been organizing language models last year, and we went to large language models this year, essentially because of the advent of ChatGPT and GPT-4. And we are also organizing a special issue on these large language models, specifically for the health aspect in the ACM transactions on health. And with this, thank you all for listening. I open to any questions you may have.
Thank you, Professor Gar. I think we are almost out of time, but we can open for one quick question. Is there any question from the outside audience or online? And yeah, if you don't have any question, we will send you the email of Professor Gar after this event. So if you have any question, you can just email Professor Gar to have further discussion. And we will also probably because we will already record the video, probably we will put the video online for Professor Gar with PPT summary. Okay. Thanks. And we will so we don't have any break right now, so we will directly move on to our next speaker. If you want to go to have a coffee break, you can just go ahead. No problem. But we don't have any break right now. Just directly go to the next speaker. So let me introduce our next speaker, Dr. Xiangshun Li. Xiang Li is an assistant professor at the Massachusetts General Hospital and Harvard Medical School and an affiliate faculty member at the Kempner Institute for Natural and Artificial Intelligence of Harvard University. Dr. Xiang Li's research focused on artificial intelligence foundation models for analyzing multimodal healthcare data. He also leads the effort to develop medical informatics systems for smart healthcare data management and data deployment in the clinical workflow. He has published over 100 papers in scientific journals and conferences with an H-index over 31. He is also the founding chair of the International Workshop on Multiscale Multimodal Medical Imaging. The short name is MMMI. And his title of the talk will be A New Perspective of Human-Centered Interaction, Human-Computer Interaction in the Era of Large Pre-trained Models. Let's welcome Dr. Xiang Li.
Thank you so much for the introduction. Let me share my slides. Wait a minute. Here we go. So can everybody see it?
Yeah, we can see it.
Great, great. So it is my honor to be here today in introducing our latest works with regarding to the large pre-trained model and combining with our investigation into this topic, my vision about how the interaction between human and computer will be involved in this new era. So as introduced just now, I am Xiang Li from Mass General Hospital and Harvard Medical School. So you can reach me at my email, and my informations are also updated on my homepage here. So before we dig down into the large pre-trained models, first of all, let's think about the previous eras of the research, that is deep learning. So think about what deep learning has brought to us, and which consists of, to my opinion, most importantly, the concept of representation learning, which is very revolutionary by the time the deep learning emerged, because people realized like the representation of the features and how it can be learned from massive data using a complex low to high level of abstraction are more important than the model alone. And also, the deep learning teaches us about the importance of model size and training data size. And as model goes deep, we finally observe that the parameter size is no longer an issue, but rather a blessing for the model generalizability. While at the same time, of course, a larger model will require a larger training data size, which makes capable due to the advancement in the big data community. And finally, the deep learning offers us a new paradigms, actually several new paradigms in the machine learning, especially the self-supervised learning concept. Well, on the other hand, well, we have seen deep learning in generating a lot of productivity in our daily life, but whether it is revolutionary way of life as it's supposed to is questionable, at least to me, because we are working in the healthcare community. So we've seen very limited application of deep learning in healthcare. To us, for the medical imaging analysis, almost very limited to the image recon, which is not completely replace the traditional recon method, while at the same time a slight few applications of the image analysis, but not too many. So that makes me think like whether the era of the so-called large pre-trained model will have the same fate of the deep learning, where it is promised much more than it can actually do so. But that is the whole theme of this talk. So let's first go to the concept, the definition for the artificial general intelligence, where before the emerge of the ChatGPT, people are presuming that there could be a hypothetical computer program that can perform intellectual tasks, while at the same level or even better than human. Well, after we have ChatGPT and especially GPT-4, we found almost all of these tasks can be done on a certain level by GPT-4, which is very astonishing to me, because initially I was personally regarding the GPT-4 or ChatGPT as a generative model, which is what it is. It is a generative model. But after using that for more researches, I realized it is not generative model itself, but rather it can do very good NER, naming entity recognition, very good reasoning, or even very complex planning works as well, which we utilize these kind of utilities in a lot of our researches, which I will describe later. So it at least for certain tasks, it has given me the impression that it is intellectual. Well, be able at least to summarize, utilize, and present the knowledge in a very meaningful way as a human. And at the same time, usually we call it foundation model for the LLMs, and also large pre-trained model as well. And because the key idea is we can use this model for a lot of tasks as the foundation of the so-called downstream task. So this is a term popularized by the Stanford Institute for Human-Centered Artificial Intelligence, well, several years ago, actually, before the emergence of the ChatGPT. And so actually, if we think about the definition of the foundation model, we can regard ResNet as a foundation model, because we very seldom just use ResNet for its original purpose, but use ResNet as an embedder for the downstream image analysis tasks. But on the other hand, usually we think like GPT-3 or BERT as the foundation models because it really offers us the capability of enabling the downstream tasks. Without them, is almost impossible. So first of all, it needs to be trained on very broad size data at scale. Really implies the data is annotated. Otherwise, the scale it is not scalable. It is not scalable. And so that incurs the authorization of the self-supervised learning, where we mask a certain part of the data. So secondly, it needs to be immediately applicable to unseen data and labels for sometimes or even more new tasks. So in medical imaging, we already seen this kind of foundation model for the multimodal across model analysis, as seen here from our good friends at CMU. So the segmentation task can be trained and applied for many types of image modalities. So we call it zero-shot learning capability. And certainly it is a foundation for the downstream tasks. And usually in healthcare, we can come up with like hundreds of downstream tasks, solving very domain-specific and patient-specific problem with a smaller sample size. But with the help from these foundation models, we can better distillate the knowledge from the model itself and then apply that to the data, and so to make this downstream task enabled. And finally, the foundation model is large. So that is both the good part and the bad part of the foundation models, because the large model size gives this unprecedented power in capturing the data and knowledge associated with them. On the other hand, of course, as the model becomes larger, even deploying it is becoming challenging, not alone trying to train that. So as I mentioned, because of this higher cost in deploying, training, and using the foundation model from both a hardware and a human resource perspective, actually it is making the whole ecosystem of the machine learning community slightly worsening, at least to my understanding. Then for certain applications, as we've seen so far, it is limited to certain tasks. For example, the SAM. The segment anything model is only for the segmentation, which is quite opposite to what a foundation model is supposed to do. And finally, it is to me a very big problem so far is we are not very sure about for specific tasks if we want a good foundation model or a good large pre-trained model. What is the size of the data needs to train it, and what is the model size that needs to capture the all the knowledge and concepts and relations within that specific field, and this kind of thing needs more theoretic investigation into it, which is largely underrepresented in the field. And foundation model is supposed to access to knowledge in specific domains, but most of the current models are general purposed, which make them less powerful in, for example, healthcare. And so that's also the motivation we are developing our own large language models and and other types of large pre-trained models using our private data. And finally, the integration of multimodal data. We have already seen GPT-4V, which can give the language description of the given image, which achieving kind of like this multimodality interoperability. And so, but we are expecting more for the multimodal foundation modeling. And also one key here is, especially in healthcare, the multimodal data can be paired. That means for specific patients, we have all this modality, and sometimes unpaired. That means we have more, for example, clinical nodes in this whole hospital than the number of images, than a specific type of images. But we want a foundation model that can process all of those together. And also, the foundation model changes the way of the interaction between human and computers, which is related to the theme of this workshop. So this in-context learning or the prompts are really powerful in its way of outlining how the model behaves based on a in-context way of providing the new samples. And so that is contrast to the traditional user interaction design paradigms. And on the other hand, that also makes all the current way of performing human-computer interaction kind of like obsoleted or out of dated because of the importance of the in-context learning. So we've seen like ChatGPT is very successful because the chatting is a very natural way of providing the in-context data to the model. But for a lot of other tasks, performing this in-context learning needs more systematic design for how to allow better human-computer interaction. And this is a description of the in-context learning. I'll skip it because we are running out of time. And also the limitations in the current UI design, which I will again